Okay, welcome everyone to the third day. So, so we will start with introducing polytopes, which will be the focus of Rekha's lectures for today. So, I'll introduce polytopes and give the basic definitions, and we'll see some examples later. Okay, so that's the plan. Okay, so to begin with, we define what is called a closed half space. Oh, I should say that in case you are not familiar with polytopes, there's a very nice book by Ziegler called Lectures on Polytopes, where he introduces where all of this material is there, so you can take a look at it. This also has things like Farkas lemma and Carathéodory's theorem, which we saw yesterday. Okay, so it's a very nice book. I highly recommend it. Ziegler, Gunther Ziegler, he's a German mathematician, quite well known. Okay, so a closed half space in RD is a set of the form x such that a dot x is less than or equal to z for some a in RD and z in R. Okay. So what you should think of is, so this a dot x equal to z is a hyperplane in general, like we discussed that yesterday. So the A is the normal to the hyperplane, and so let's do an example. So so something like this. So you draw this line, and everything on one side of it is a half space. Okay. So this is the hyperplane. In general, we want to give ourselves the freedom of not. This need not be a subspace because it need not pass through the origin. Right? It just, so this, if, okay, I'll make that comment in a second. So, if you wanted the other side, you would change the sign of A. Right? So, you would take the other normal. So, A is this side in this case, otherwise, A would be, you would just take the negative of it, right? So, and so this line is AX, A dot X equal to Z. Right? Okay, so and a half space is linear if Z is equal to 0. Right? So in that case, it passes through the origin, and in that case, it's a vector subspace. Okay, so before we get to polytopes, I want to say something. I want to define something a little more general. A polyhedron is a set of the form x in RD such that AX less than or equal to Z. So I'm underlying vectors just to prevent confusion. So here Z is a number, here Z is a vector. I hope I'll specify what these things are, where A is in R M cross D and Z is in R M. Okay, so we have some rectangular matrix, we are multiplying by x, and we are demanding that it be less than this vector component wise. So this is a polyhedron, it may be unbounded. So for example, you could have something like this. Oh, I wanted it to pass through the origin, but okay, it doesn't matter. So it could be something like this. It could be a cone, for example, right? So cones are examples of polyhedra. Okay, but it could be more complicated. It could have, I could have another line going through here, and it could be part of it. Okay, so okay. Okay. We will work with convex sets, so it's but
You are talking about vector inequality, you mean component-wise?
component-wise, yes. Yeah.
Are there any restriction on A other than it is rectangular?
No restriction. Yeah. In general, you mean rank or anything? No. If it has lower rank, it could be sitting in a smaller subspace. But as of in general, there is no restriction whatsoever, and it may or may not be bounded. Okay, so this may be bounded, may or may not be bounded. Yeah.
So it is like simultaneously in a set of K, it is an intersection of sets of that form, right?
Yes, exactly. So it's right, exactly. Thank you for. Yeah, I should have said that. So this you can think of as intersection of half spaces. Okay. Finitely made. Yeah, because A is a finite matrix. Right. So there are m intersections. So you have m such conditions, and you look at it. If I had one more such thing, one more line like this, and forcing it to be inside, then it would be bounded. Otherwise, it may be unbounded. There is no restriction here. So convexity is going to be important. So I'll just define it formally. So a set K in RD is said to be convex if for any xy in K the line segment joining x to y belongs to K. So more formally, the set lambda x plus 1 minus lambda y, where lambda belongs to 0, 1, is contained in K. Okay. So, for example, this is not convex. Why? Can anyone say? Yeah. So if I take this line joining these 2 points, so if this is x and this is y, so the line joining them goes out of the set, right? So this is not convex. Okay. All right. So we are going to talk about convex hulls. So okay. So I'll define the convex hull formally. So again, let K in R be a subset of RD. The smallest convex set containing K is called the convex hull of K. And you'll also use conv of K as a notation. Yeah. So we'll denote it conv. Okay. So we will see, Rick has prepared examples of this, so we will see this very soon. Okay. So now we come to polytopes. So right. So So, how should I say it? A set, okay, so let V1 up to Vn in Rd be some vectors, okay. The convex hull, so it's important to be that we have only finitely many vectors. So the convex hull of V1 to Vn is a polytope. So P is conv of V1 to Vn. Okay. So let's do some examples. So let's first take n equal to 2. So we'll work in R2. So this is a point 1, 1, and this is a point 0, 2. What is the convex hull of these 2 points? It's the smallest convex set containing those points. So what is the smallest convex set? I mean, certainly I can draw this square, right? It contains, I mean, it's convex, it contains those 2 points. I can draw a circle, I can draw many things. But what is the smallest? What will be at the intersection of all of them? The straight line, yeah, exactly. So, oh, maybe I should use another color. Okay, so that is the convex hull in this case. So here, sorry, yes, thank you. Okay, so let's now add one more point into the mix. So I'll again take these points. So 1, 1, 2, 0, and now I'll take 2, 1. I have 3 points. Okay, so these are on the same y coordinate, these are the same x coordinate. What is happening here? So what is the convex hull of these 3 points? Triangle, exactly. So, but it's not just the boundary of the triangle, it's the entire thing. Okay? And let me do one more example. Okay, so suppose I have some funny shape like that. So this is a set S. Okay, what is its convex hull? How is it going to look like? So think of all possible, any line that's already in the set S is unaffected, right? Because then it's all. So you should think of lines, I mean lines joining points that do belong to the set where the line goes outside and include all those points. So which line do you think, can you think of a line here which does not belong to the, yeah, so if you join something like that, it's outside, right? Any other kind of line? Below. Something like this, right? So we should include all of those things. So what will you get? I mean, it's nothing very special. No, it's. Sorry? Yeah, like a stadium. Okay, that's it. Yeah. So we will draw these kind of tangential things which will cover all of these and everything inside will become. Okay. Okay, so once you include things like this, then all lines which were going outside. So the problem was only over here in this things with kind of inward curvature, right? So we include all of those. So that is convex. Okay.
Arvind, maybe this is a good one to ask. Can you cut this out with half spaces as well?
This for this set. Yeah, so can you, right. So question,
So
can conv of S be cut out, be the intersection of half spaces? What do you think? Huh? Not possible. Anyone thinks it's possible? Why is there a problem? Right, because of the curvature over here. So, well, in some sense, the question is ill-posed. I mean, it is the intersection of infinitely many half spaces, but I meant finitely many, of course. So here, anything which has a curvature will cause problems. You'll have to have infinitely many things to combine all of those curved regions, right? So okay, so that's the problem. Okay, so let's do a three-dimensional example. So this was d equal to 2, and here this is d equals 3. Let us take okay, so I'm asking for S equal to conv of the following. So I'll not write, I'll not put parentheses, I'll just write triplets. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1. What is this going to be? So this is x, y, and z. So I have the origin over here. I have 1, 0, 0 over here. So I have the E1, E2, E3, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then I have 1, 1, 0, and then I have 1, 0, 1. Sorry, I'm not very good at drawing these things. Right? So what do we get? The cube. So the convex hull of this is a cube. Is a three-dimensional cube. Cube in cube. Okay, and in general, in Rn or Rd, if I take conv of 0, 1 to the d, so you know this notation. This means d tuples of all possible, I take all possible choices of zeros and ones in those d positions, right? So this is the special case for d equals 3. There are 8, 2 cubed equals 8 vectors. So here conv of d is 0, 1 to the d is the d dimension. Okay. So there are so other than the cube so the cubes are important examples of polytopes. They have the property that well, every vertex is I mean, how should I say this? Yeah. So every vertex has neighbors which are their d neighbors in d dimensions, right? So there's a special name for such polytope. Okay. So another important class of examples is the what is called the d simplex. So delta d is the convex hull in E1 up to ED plus 1 in RD plus 1. Okay, so everybody knows what EI is? Yeah, so where EI is the unit vector in the ith position. And this is in RD plus 1. Okay, so what does delta 2 look like? So delta 2. So you take E1, which is this one, E1 and E2, and you take their convex hull just like we did before, and you get the line. And so this is delta 2 and delta 3. Okay, again, I will not be able to draw very well. Sorry? Oh, sorry. This is delta 2 should be in R3, so this is delta 1. This is the 1 simplex. Thank you. And this is delta 2 now. This is the 2 simplex. So I'll take the convex hull of E1, E2, E3. So it will be a triangle but in 3 dimensions. Okay? So it will. Okay, it's a triangle. Can everyone see why they are in the same hyperplane? Well, okay, in general any 3 points will be in the same hyperplane, but here the hyperplane will be where the sum of the coordinates is 1, right? Because all of these satisfy x plus y plus z equal to 1. Right? So, okay, so now I want to define the dimension. The dimension of a polytope is dim of P. This is the dimension of the affine hull of P. So if I take, so P is a set, right? So it lives in some hyperspace, it lives in some affine hyperplane. So like in this example, so in this polytope, or this, okay, this is trivial. In this polytope, it lives in a one-dimensional space in R2, right? So its dimension is 1. Okay, because it's one-dimensional, because if I translate it, I get back a subspace, and for subspace we know the dimension, right? So I mean, we all know the dimension of a subspace. So that if I translate a subspace, the dimension is unchanged, right? So the dimension of an affine space is the same as the dimension of the corresponding subspace I got by translating it. Okay, so this is what it means. Okay, so right. So now, so there's an exercise. So check that polytopes are 1 convex. This is almost by definition because it's the convex hull of points. Two, that they are bounded. Bounded means, I mean, one can define it topologically, but also there's one way of defining bounded, which is that there is no ray. It does not contain a ray. So a ray is ray is a set of the form. So maybe I'll write. Is that what you had in mind about bounded?
Yeah, or just put it in a sphere.
Okay, yeah, we can. That's another way of saying it. There's a sphere that contains it, or you can say that it does not contain a ray. That you take a point and you take a vector, and which runs off to infinity in that direction. That ray, the set should not contain any such ray. So then it becomes bounded, i.e., but is contained in a large enough sphere. And 3 is that it is closed. Okay. Right. Okay. So let's go back to the simplex. So this 2 simplex is not. I mean, it's contained. So delta 2 is inside the line, inside the set x y z, such that x plus y plus z equal to 1. Right. Right. So now if I translate that to the origin by changing 1 to 0, then I get a 2-dimensional space, right? Because x plus y plus z equal to 0, that means you have only 2 free parameters. For every x and y, I know z, right? So this is a subspace, and for subspace we know what the dimension is. You can give two independent vectors that span this space. So this has dimension 2. I mean, you can also think of a line in R3. Right? So in R3 I can take, if I forget this third point, I just have these 2 points, then it spans a line, right? So I mean it's a line segment, but it's affine. It does not pass through the origin, right? So I can translate it so that it passes through the origin, and I can extend it in all sides to get a subspace. Okay, so. Sorry? Okay, let me just formally define it then. Okay. Yeah, so the affine hull is defined, and but the dimension is. Yeah, so it's the dimension of the affine hull.
Correct.
So affine hull is a translate of a subspace. Affine space is a translate of a subspace, and you just translate it. So given an affine space, you translate it back, you get a subspace, and we know from linear algebra what's the definition is. Okay, so that's the main idea.
By closed, you mean that the polytope is closed, you mean that
Yeah, contains its limit points. So in the sense of topology, yeah, and that's because we are okay. So we are including the points, right? And the segments that contain. So we are including the boundary. So Rekha has prepared this Mathematica notebook demo. So in the first example, we are taking. Maybe I'll increase the font size. Okay, so we are taking inside the unit square minus 1 1, inside the minus 1 1 unit square we are taking 50 points. Is that right? Is that what that could? Yeah. Okay, and then curl.
So from, I think, yeah, that's right. Sorry.
Because from minus 1 to 1 you are taking 50 points in a two-dimensional array. Yeah. So, and curly R is the convex hull of those things. Okay, so curly R is going to be the blue thing. Okay, so now this was random, so this was when she generated it. When I'm going to rerun this, the points are going to change. Okay, so now it changed, right? You saw there was a slight change. So the
What do you mean by between minus 1 and 1? You mean the interval or?
Yes.
yeah, minus 1 1 squared. So
Yeah, that is in 2 dimensions.
yeah, this is in two dimensions. So the square with minus 1 here and 1 1. Okay. Okay. So this overlays. So the command overlays the convex hull in blue with the points in black. So you can see most of the points are redundant, right? I mean, it was enough to just take the convex hull of this, all that, right? So if you take too many points, this will happen. Okay, so here's a beautiful example of a teapot. Okay, it's pulling it from the internet, I think. Sorry? We'll see. Oh yeah, do you think it's convex? Okay, why not? That handle, so if I take 2 points in the handle, I mean one above, one below, and I join them. So actually I can, I think, move it around, yeah.
It doesn't have a bottom.
Bottom, yeah, so it's a useless teapot. I mean, all the tea will fall out from this. Yeah, okay. Okay, so now we are going to do the convex hull of this region. So R is the convex hull, and now here's what it looks like. You see, so this was the handle, and this is the spout, like in the poem, the nursery rhyme. And now you see all of the things.
And the bottom is covered.
Now it's a useful teapot, I guess. Yeah, okay. But you can't see it, okay. No, now you can. You can't pour into it. Yeah, true. Yeah, it's closed from all sides. So it's again useless for a different reason. Okay, so you see, so basically what happened is all of these lines that were causing problems have been created, and you took all those things and you sort of covered it in a cocoon. Okay, so now let's do. So now in 3 dimensions we are looking at some other collection of points. Okay, now P is the convex hull, and now let's see what this looks like. Should I first try and draw it on the board, or?
It's a little complicated.
Yeah, okay, fine. So let's just see, break the suspense and see what it looks like. Oops.
Maybe we should change the color from orange to something else. I don't know, because it's hard to see here.
Okay, so what, purple? Pink?
It's usually good.
Okay.
Oh no, it's not good.
Magenta? Blue. Yeah, okay. Is this better?
It might be easier on their old computers, but
Yeah, on my computer it looks good, but here the.
green is a little more.
I have to make out here. Some dark color, maybe dark blue? No. Let's try magenta. Is this better?
We can just move it around in case they see the general idea.
Oh, I think maybe because
Play
opacity.
with the opacity too.
Is this better? Okay.
Yeah, I think this one you can just do on your own computer and see.
Yeah, you
But
can.
you can see, right? The flat sides.
Yeah. Maybe while I'm moving, you can see it better. Yeah. Yeah. Okay. So things can look quite complicated. Here is another convex hull of these points. I'll increase the opacity. So this has a nice symmetry. Can you see it? Yeah. Okay. Okay. So, right. So these are some nice examples that Rekha made. I'll share this with you in your folder. It's there already? Okay. Affine hull is a affine space. It's infinite.
Convex is bounded with
Yeah, convex hull of a finite number of points will be bounded. Right? So, but affine hull you really think of as a translated subspace. Okay, that's how you should think of it. Yeah, you allow lambdas to vary all. So you instead of taking between 0 and 1, you allow them to go in all, or vary in R. So for example, if you have two, like in x, y, if you have 2 points, instead, if we just took 0, 1, we get the line segment joining them, and you want to extend it in all directions, so you R, just change 0, 1 to R. Right? So that will. It's not a ray, because ray is just one in one is infinite in one direction. We want the whole thing, so by infinite, so on both sides. Okay. In 2 dimensions, we want infinite everywhere, right? So the affine hull of this surface of the table would be the whole thing going off to infinity in all directions. Yeah, that in that example, the affine hull of delta 2 is this entire hyperplane. Think of this going off to infinity here, 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 everywhere. Okay? Yeah. All right. So an important theorem about polytopes, or an important property, is that they have 2 representations. This we saw yesterday also. One is called the V representation. So here P is the convex hull of V1 to Vn in Rd. And the second thing is called the H representation, or hyperplane representation, or half space representation, whatever you like. So this is P is X, the set of X in Rd, given by Ax less than equal to B. Right, this is what I had said earlier. Right. So here you think of this as an intersection of closed half spaces. Okay. So for example, for the 3 cubed, we saw for the 3-dimensional cube, this is the V representation, right? Can you think of what is the H representation? What are the planes? Yeah. So we have to pin down which hyperplanes we are talking about.
X equal to 0, y equal to 0.
But those are the hyperplanes. But what are the half spaces? That's right. So let's do that. So I have x1 greater than equal to 0, x2 greater than equal to 0, x3 greater than equal to 0. So that will place it in the first orthant, right? In the thing that's coming out of this the board. What else? X3 less than or equal to 1. What is that saying? So that's saying this is my x3, z is x3. So it's saying it's below this, right? So it's saying it's above x3 greater than or equal to 0, but below x3 less than or equal to x3 equal to 1, right? So between 0 and 1 in x3, and the same idea in all of them, right? So x1 less than or equal to 1, x2 less than or equal to 1, x3 less than or equal to 1, right? So we can draw. So maybe it's also helpful to see how you would write it as ax less than or equal to b. So let's do that. I mean, you might be getting confused as to what do you do with greater than and less than, right? So the h. So we will write this as. So I will write a 6 by 3 matrix. There are 6 inequalities, right? And we have the vector is x, y, z, right? And I have less than or equal to. So now let's see. So I want to say x1. Okay, let's do because this is less than or equal to. These three are naturally less than or equal to. Let us just write those first. So how would you write? Okay, maybe to avoid confusion, I'll write x1, x2. Okay, so here I'll have a 6-dimensional vector. Okay, so what is the first row? 1, 1, 0, 0. Right, so x1 less than or equal to what? No, we are looking at this bottom one, because it's less than or equal to 1. Right? So this says x1 less than or equal to 1. Next. Yeah. Less than or equal to 1. And then last one is less than or equal to 1. Okay, so I'm running out of space. Okay, so let me do it at the end. Now I want to do this top row. Right. So we want to convert these greater than equal to into less than equal to. We cannot touch x, y, z, right? I mean that vector is fixed. So what do? You negate the coefficients. So here in x1 greater than equal to 0 is the same as saying minus x1 less than or equal to 0, right? So that's the same thing. So how do you say minus x1 less than or equal to 0? Less than or equal to 0. And similarly 0 minus 1 0, that's x2 minus x2 less than or equal to 0, and minus x3 less than or equal to 0. Okay, so this is the H representation for the cube. Okay. On B, so we'll come to that. Yeah, this is quite easy. So what do you think, maybe I ask you, what do you think you will have for the simplex in general? So simplex is the convex hull of d plus 1 points, right? The d simplex. How many? So in this case, okay, this case is silly. In this case, how many hyperplanes do you need? Okay, so okay, so this is confusing for multiple reasons. So maybe we should not do this yet. See, the problem is that this lives in a lower dimensional space. The simplex, the three-dimensional cube lives in R3. but the 2 simplex lives in R3, but it's a 2-dimensional object. Its intrinsic dimension is not the same as the dimension of the ambient space. So this is a bit confusing. We'll come to that in a second. But maybe let me postpone this example for a second. But if you want to think of, let's say this example, how many hyperplanes would you need? 3. Why? What are the hyperplanes? This line, and this line, right? So in each case you will have to massage the coefficient so that it's always of the form less than or equal to, if you are writing it in this notation, right? Okay, so maybe this exercise we can do later. I'll come back to your question about how many hyperplanes would we need. But before I come to that, let me just state an important theorem which is not easy to prove, is that every polytope has both a V representation and an H representation. But it's not easy to go to prove this. You would have to say that if I give you like a polytope this way, as we defined this as a convex hull of points, I would have to give you an H representation. So I have to give you the hyperplanes. But how do you do that in general? It's not so easy, right? Even for this cube, okay, we know it's a cube, but how do I know which hyperplanes to take, right? I mean, I cannot take the hyperplane consisting of these, this and this, because that will cut the polytope, right? So we want to take what are called supporting hyperplanes. We want to take hyperplanes where the polytope lies entirely on one side. Okay, so I should take the hyperplane y equal to 0. I should not take the hyperplane which x plus y plus z equal to 1, for example. That will contain these E1, E2, E3, but it will cut the cube, right? So we should be careful. How do you do that systematically? It's not so clear. Okay, so there is a technique called Fourier-Motzkin elimination that will do it, but that's kind of hard, and we don't want to get into it. So the proof is there in the book if you are interested. Okay, so for now we'll just believe this theorem that you can either, and this is in the spirit of other theorems that Rekha mentioned yesterday, that there are 2 ways of looking at many objects, in particular polytopes, right? So we have this V representation and we have this H representation. One is good for which membership, yeah, and one is good for generating samples of points, right? So if you want to know if a particular point is in the polytope, you just plug it in here. In the H representation, you just check. And if you want to generate a bunch of random points, you have the V representation, you generate a random sample between you take numbers which sum to 1 and you, let's say, n numbers randomly which sum to 1, and you take the appropriate linear combination, you get a point, right? So you can generate that very fast. So that's why these things are important. All right. So okay. So in general, okay. So for the D cube, the V representation has how many points? How many points do we have for in the D-dimensional cube? 8. No, D cube. 2 power D. So has 2 to the D points. Right? It's a convex hull of 2 to the D points. And the H representation has how many hyperplanes? No, D-dimensional cube. How many? 2D, right? For each, so if you go back here, for each coordinate we said greater than equal to 0, less than equal to 1, right? So for each coordinate independently, so this has 2D inequalities or hyperplanes. So this was a 6 by 3, that's 2D by D, right, in general. Oh, 6 by 1. Okay? Alright. So let's do one more example of so write the H representation for the polytope, which is the convex hull of 0, 0, 1, 0, 3, 2 and 0, 2. Can you try? So plot these points and see if you can. How does the shape look like? Does it remind you of, what's the name for such an object from high school geometry? It's a trapezium. So 0, 0, 1, 0, 0, 2 and 3, 2. Okay. So you got it? What are the hyperplanes? Or let's just write down the inequalities. So let's write in x and y. So what is y greater than equal to? Y greater than equal to 0. X greater than equal to 0. Y less than equal to 2. Right, so this is 2 and this is, yeah, okay. Sorry? X minus y? This line, right? So we got this line. So this we got, this we got, this we got. So we need to get this line. So you are saying x minus y. So the line joining 1, 0 and 3, 2 is what we are talking about. So the line joining them is x minus y equal to 1. And now which way do we want it? Yeah, because the origin is on this side. So we want less than equal to. Yeah, so these are the. So 2 dimensions is somewhat special in the sense that if you have a convex polygon, then if it's an n-gon, you also have n hyperplanes. That's kind of too simple. I mean, when you go to higher dimensions, things get much more complicated. Okay. So, alright. So now let's talk about faces. So let P as usual be the convex hull of V1 up to Vn in Rd. Okay. A set F in Rd is a face of P if F is the intersection of P and H, where H is a hyperplane, so X in Rd, such that A dot X is equal to C, is a hyperplane. And P is either contained in H plus or P is contained in H minus. So H plus and H minus means you're on one side of the hyperplane. This is what we saw yesterday as well. So such hyperplanes are called supporting hyperplanes. So for example, so we can take the same example. So let's take something like that, and let me use another color. So what is an example of a face here? So I want a hyperplane which intersects, I want to take the intersection of a hyperplane with P. So for example, if I take this hyperplane, what do I get? The empty set. So the empty set is also a face. Okay. So that's kind of stupid example. But can we have a simpler example or more useful example? Y equal to 0. So if I take y equal to 0, I take this, right? So maybe I should use another color. Okay, so this, sorry, it's okay, both are okay. So x equal to 0. So this is an interesting hyperplane because the polytope lies entirely on one side. Okay, where I also include the 0. Okay, that's a lot. And the intersection is this bit over here. So this thing is the face. Okay, P intersection that hyperplane. Okay, is a face. But this is not the only one. Similarly you can get all these hyperplanes, right? So all of these hyperplanes, if you intersect, you get faces which are one dimensional. But I could also intersect with this face, with this hyperplane. What is the intersection then? Is a single point. So a single point is also a face. Okay? So the empty set is a face, is always a face. Empty set. In this example, we get vertices. So this is always vertices. Maybe we have to find it. Yeah. Okay. So empty set when H does not intersect P. Since P is a polytope, it's bounded, so you can always find a hyperplane far enough which does not intersect P, right? So such hyperplanes always exist. So this will always be a face. P itself will be a face. So if P itself is a face, when we take A to be 0, right? When we take so then there is no condition here. A equal to 0 and C equal to 0. Okay, okay. This is the 0 vector and C equal to 0. So if I take A equal to 0, the 0 vector, and C equal to 0, then every x in RD satisfies this. Right? 0 times x equal to 0 is satisfied by every x. So that's all of RD. So P intersect with that is P itself. So P is also a face. Again, it's a kind of degenerate example, but these are two important examples of faces. And so these are called improper faces. They are always there and they are kind of boring. So we are interested in the proper faces. Okay, so now every face, if you think about it, is itself a polytope. Okay, so since P is convex, every face is going to be convex. I mean, one has to argue, but it's not hard. Exercise, every face is a polytope. It naturally has lower, I mean, the proper faces naturally have lower dimension, right? So a vertex is also a face, is also a polytope, sorry. Right, a single vertex is a polytope because there is nothing to check. I mean, it's convex because there's nothing to do, right? Vacuously. So one can talk about dimension of faces, right? So about the dimension of a face. And so for example, for example, or maybe notation, a face F with dimension F equal to 0 is called a vertex. These are points, these are extremal points. These are the points in the vertex, in the V representation, these are the points that you are taking the convex hull of. A face F with dimension F equal to the dimension of P minus 1 is called a facet. It's a special kind of face. These are the maximal proper faces, maximal dimensional proper faces. Okay? And facets are going to be important, and let's see why. So, okay, so let's draw this polytope. Which you might see if you go to Egypt. Okay, so it's a pyramid. Okay, so So this is our P. This is in R3. Right? I hope the picture is clear, even though my drawing is terrible. Okay, so let's use some colors. So these things in orange are the vertices of P. Okay. Can you see an example of a facet? What is a facet here? Bottom square is a facet, yes. But this is also a facet. So how many facets are there? Facet of P. But is there anything else? Are there any other faces? Proper faces? Edges, yeah. So can you think of a hyperplane that gives, well, the facet is given by a hyperplane itself, right? That hyperplane, the supporting hyperplane of that. But what, and vertex I showed you like in that example, how will you get edge? No, but how will you get it from the definition? No, but I'm asking for a hyperplane. So the definition says that F is P intersection H. So if you claim that an edge is a face, you have to produce a hyperplane which satisfies the definition. But which hyperplane? I mean, if I take this bottom thing, it doesn't only contain that line, right? It contains that entire bottom face. I want a hyperplane. No, that's not a hyperplane. A hyperplane by definition has codimension 1. It's a plane. In R3 it's a plane. You cannot take a line in R3.
Intersection of two hyperplanes, so we need a hyperplane that is also intersecting those two. I mean, these hyperplanes are lower.
Yeah, so I think you have the right idea. Which hyperplane? So you take something in this and take the vertical. It won't be tangent. It's important that it not be tangent, right? So it will touch, it will intersect P only in this line. It will not intersect it in this face, it will not intersect it in the bottom face. It will only intersect at that line. Okay?
Even in edge, there are only finitely many facets with that edge on it, and there are infinitely many hyperplanes passing through that edge. So you have a choice.
Correct. So you can, so like she said, you could take the vertical thing passing through here. So for example, imagine this pyramid were here, right? So imagine it was somewhere here. Then I take this vertical thing that just touches this edge. It does not touch anything else. Okay? But I could also take something at an angle and it would still touch the edge. There are infinitely, as she said, there are infinitely many. But you have to, anyone will do. I mean, one has to be careful because the polytope may be complicated. So something orthogonal might intersect in a face, a non-trivial face. So we don't want that, right? So it is possible to do it. So all, even edges belong. So let me draw that. So these green things are also faces.
Dimension of the face is dimension of that hyperplane.
Dimension of the face? No, hyperplanes are always codimension 1.
That's what it's.
So dimension of the face is the dimension of the, because the face is itself a polytope, it's the, and we have defined dimension of a polytope, you use that definition. Okay? So this is a face of P, which is an edge. One doesn't talk about edges in general, one can, but I mean, mostly one needs facets and vertices. So before we break, I'll just answer your question. So the H representation of a polytope is determined by its facets. Okay, so right, you see, so each facet is the maximal thing. I mean, if the polytope lives in has the same dimension as the ambient space, then hyperplanes determine the facets, right? So they will give you the H representation. Okay, and let me come back to this simplex issue in just 2 minutes. So for the simplex, there's a problem because it doesn't live in its natural space, right? It's a D. The D simplex is a D-dimensional object, but it lives in RD plus 1. So one needs. So for example, so let's look at the 2 simplex delta 2. Right? So we had this. Right? So it lives in x plus y plus z equal to 1. Right? So so in the H representation we need, so here we need to say x plus y plus z less than or equal to 1, and we also need to say minus x minus y minus z is less than or equal to 1. Or in other words, x plus y plus z is greater than or equal to 1. So we need both these hyperplanes. Thank you. Right? So then one says that x plus y plus z is less than or equal to 1. One says x plus y plus z is greater than or equal to 1. So then that forces it to lie in x plus y plus z equal to 1. So this is what you would have to do if the polytope lives in its dimension is smaller than the dimension of that space where it is sitting. Okay. So one can do it also, and then A is linearly different. Yes. That's fine, but that's okay. Yeah. So then 2 rows will be the same. I mean, up to sign. But it's anyway, right? I mean, even in that example, the 6 by 3 example which I just erased, it can have rank at most 3, no? It cannot have rank 6, so it's okay. Yeah? Yeah, you will have more constraints. I'm not writing them down, but there are others. But this is the key I wanted to illustrate, which is new for this, which we did not see earlier, right? Because, so you have to, if the polytope if we are in RD and the polytope has dimension k, which is less than D, then you have to keep slicing it down by writing so many inequalities until you come down to dimension k, and then you put the natural inequalities. Right? Okay, so let's stop for now. Yeah. Yeah. This one? This one? Yes, that is. Sorry?
It is not a case, then there is a negative vertex only.
No, but this condition has to be satisfied. It should be a supporting hyperplane. The polytope should be on one side of the hyperplane. Okay, otherwise we cannot. I mean, this is part of the definition. You cannot cut the polytope. Okay.
Till now we only know that to separate these points B or the other ways.
Say that again.
To prove every place is a polytope. If we want to prove every place is a polytope.
Yeah.
Right now we only know only one definition. We have to produce this VAs.
No, but you can assume the theorem that every polytope has a V representation and an H representation. Okay, and I gave you a hint over here.
You can give a H representation based on
Yeah, you could do that. Yeah.
I have one question. In the other example you showed where we had a curvature,
Yeah.
it had infinitely many hyperplanes in it.
Yeah.
So still the theorem holds.
No, no, no. No, no, no.
Now how does that there then how do we talk about convex hull? If the convex hull is having kind of a curvature.
I mean, there also you need infinitely many vertices, right, to take the convex hull off. So, no,
If it's a curved surface, not a polyhedral surface.
right. Then you can also talk about the convex hull of, for example, if you're talking about the sphere, you take the convex hull of the surface of the sphere, you get the whole sphere, right? I mean, which is also an infinite set. In both cases, you will have uncountably many objects to take either the H representation or the. But we are not going to talk about that, right? I don't think we're going to talk.
So for general sets, there's something called extreme points. So like the picture, can I just draw?
Yeah.
So for example, if you took this picture, okay, I'm just drawing that piece in orange for a minute. This is a convex set, right? So if I wanted to write this a convex hull of points, you definitely need every point on the semicircle. Then you need this and you need this, and that's enough, right? Those are called the extreme points. And so it's true that every convex set is a convex hull of its extreme points. And the extreme points are defined as points, points that cannot be written as a convex combination of other things inside the set. Make sense? So now here we have infinitely many extreme points and also infinitely many inequalities, because for this, here I need only 3. The white part is fine. I need this inequality, this inequality, this inequality. But on the orange part, I need infinitely many, all the tangent lines that go on this.
Yeah.
Right. So it's the intersection of infinitely many half spaces and infinitely many extreme